students, today we are going to discuss about 2 plus 2 cycloaddition reaction of ketenes. So firstly, this cycloaddition reactions of ketenes are familiar with the cycloadditions of alkenes, and normally what we have up to now seen about Diels-Alder reaction and all. So just see, in case of a ketenes, we are going to discuss about cycloaddition reaction of ketene plus alkenes. So what is meant by ketene? Suppose we have this compound C double bond O double bond C and some substituent, suppose it will be a dichloro compound, then this compound is called as a ketene. You know already about what is meant by ketone. C double bond O is called as a ketone, right? That carbon if connected with double bond C. Now in this total structure you can see here, this compound is called as a keto compound, and this is from the alkene. Double bond is from alkene, so it is ene. So finally, after all, you can say it is a ketene. Okay, so keto plus alkene, it is a ketene. So in case of cycloaddition reaction of alkenes plus ketenes, you will get a cyclic product like Diels-Alder reaction and all. Suppose we have an example about this. We have a cyclooctatetrene means 4 double bond, and it is in a 2 form, that is cis form, and second one will be a trans form. Trans form will be 1 2 3 4 5 6 7, one more will be 8, so 8 carbons, and this is a trans form. Okay, here will be one hydrogen and one hydrogen will be on opposite side, so this is a trans form. Now if the cis form and trans form both reacted with ketene molecule C double bond O double bond C, suppose dichloroketene molecule, and the same will reacted with this trans form of ketene molecule, transform of this cyclooctatetrene molecule. Now you can see here, after the reaction at 25 degrees Celsius, means thermal condition is there, the product we will get that cis form compound maintain stereochemistry, and you will get the product in a cis form only. See, this compound, that is ketene molecule containing carbon-carbon double bond, and this cyclooctatetrene also containing carbon-carbon double bond. So this electrons will shift here and this electrons will shift here. It will be make a new bond between this carbon and this carbon, and there is a new bond between this carbon and this carbon. So you will get here formation of a cyclic ring, and remaining structure as it is, this carbon double bond O, this 2 chlorine atoms, one chlorine below the plane, second chlorine will be above the plane. Okay, and the remaining structure as it is, there is just only cycloaddition reaction takes place between this 2 carbons and this 2 carbons, means this is a alkene molecule and this one is a ketene molecule. From this ketene molecule we are going to react this carbon-carbon double bond with this carbon-carbon double bond. Remaining structure remains as it is. Okay, now in case of this trans cyclooctatetrene, you will get a product with a stereochemistry maintained, means just cyclic product formation takes place. This electrons will shift here, means there is a new bond formed between this carbon and this carbon, and this electrons will shift here, means new bond between this carbon and this carbon. So cyclic compound is there and remaining structure as it is, but one change or one difference between these two is, that is in case of cis cyclooctatetrene, there is both hydrogens, as it is in a cis form, both hydrogens are at the same side, maybe at below the plane, or you can show it above the plane, then just other structure will be just changed somewhat. Then in case of a trans, you can see if one hydrogen is below the plane, then second hydrogen will be above the plane, as they are in a trans position. But now the important point is, in case of cycloaddition reactions, as we are doing this cycloaddition reaction, we have already discussed in our last few lectures that in case of a cycloaddition reaction, we are doing this 2 plus 2 cycloaddition reaction, right? This 2 electrons from this one carbon-carbon bond and 2 electrons from this second carbon-carbon bond. So in case of 2 plus 2 cycloaddition reaction, we have done some table like manner result, that is in case of cycloaddition reaction of 4n and 4n plus 2 rule, that is 4n and 4n plus 2 system, thermal and photochemically, right? But in case of photochemical reaction, 4n system, this is a 4n system, 2 plus 2 electron system is a 4n system. So in case of 4n system, it is allowed by photochemically, right? We have made that conclusion that it is allowed by photochemically, but the result was it is allowed by suprafacial addition, right? If both the system or both the molecules are going to add by supra manner, then only it is possible by photochemically. And opposite way, that 4 plus 2 reaction also allowed by thermally by supra manner, suprafacial addition. But if the condition, now our condition is 4 an electron system, right? We are going to add 2 electrons plus 2 electrons over 4 an electron system, but it is happen at 25 degrees Celsius. As it is at 25 degrees Celsius, means the reaction is at thermal condition. So if the reaction is at thermal condition, the suprafacial changes to supra interfacial, right? So the reaction is allowed by supra intrafacial reaction, and supra intra means the photochemical will changes to thermal reaction. So as the reaction is possible by thermally, the product we are getting that must be formed by supra intrafacial addition. So how this condition is possible in this case? See, in case of a ketene, there is one change, that is, we have this carbon double bond oxygen, carbon double bond carbon, this like a structure in case of a ketene, right? In case of a simple alkene molecule, we have this 2 carbon atoms or any other atom. Up to now, we discuss about 1 p orbital in case of cycloaddition reaction or electrocyclic reaction. But in case of ketene, there is one change which allows this ketene to react like this. Okay. Suppose we have this molecule oxygen, carbon and there is 2 substituents at carbon. Now this oxygen has 2 p orbitals, right? And this carbon also has 2 p orbitals, and this carbon having 1 p orbital. Why? Because we have a structure like this: oxygen double bond carbon double bond carbon. Now for the double bond between this oxygen and carbon, this pi bond, this oxygen and carbon require 1 p orbital, right? And there is another pi bond, that is another double bond between this carbon and this carbon. So it will require one more pi bond or pi orbital, that is a p orbital. So this carbon containing one p orbital, and which is, right, this pi bond require one p orbital, which make a pi bond between this carbon and this carbon. Again we have to make one pi bond between this oxygen and carbon. So here will be this oxygen must contain one p orbital, which is now orthogonal to this p orbitals, right? So there will be a requirement of another p orbital. Means this carbon require totally 2 p orbitals, one for the pi bond between this carbon and this carbon, and second for the pi bond formed in oxygen and carbon atom. Now in this case we have to add another alkene molecule with this ketene. So we have this alkene molecule. One orbital of this alkene molecule will make a bond between this p orbital, and second p orbital will make a bond between another orbital of ketene system. Now as we already discussed, this reaction as it is allowed by thermally, then the reaction must be supra interfacial addition. So here you can see it is a supra interfacial addition, right? One lobe of one system and another lobe of that system. Means when both lobes of that system, one system reacting from same side, if this orbital and this orbital will make a bond, then we can call it a suprafacial addition. But now you can see in case of this alkene molecule, both lobes from the same side are going to react. But in case of this ketene molecule, this lobe from downward and this lobe from upward going to react. I mean, this one is interfacial addition, and this ketene is showing something like suprafacial addition. So this is a suprafacial intrafacial addition takes place, and this addition is only possible by this carbon or this whole system of ketene containing 2 orthogonal p orbitals which are perpendicular to each other. So they can easily make a 2 different bond between this carbon one p orbital will be there, and second p orbital will be used for to making this carbon and oxygen bond, right? So just see how it is supra and intrafacial addition takes place. Now in this case also we have to study about HOMO-LUMO concept, right? HOMO and LUMO concept means in case of a cycloaddition reaction we are going to make we are going to take HOMO of one system and LUMO of another system, or LUMO of first system and HOMO of another system. Just in case of a first reaction, suppose we have one compound which containing means ketene compound, carbon double bond carbon, oxygen double bond carbon, double bond carbon, and substituents. So to write this molecular orbitals, you have to write psi3 functions, right? Psi1, psi2, psi3. But as we have 3 atoms, so this is the middle psi function, that is non-bonding energy level. We'll go from that, and we have to distribute 3 orbitals, right, from each atom. So 3 orbitals for each atom. Then you have to distribute a node. Here we have a 0 node as a psi1 function, 0 node. Then 1 node means there is no need to draw these orbitals. You can just put a dot here. Then as this is a plus with a node, you will get a change in the sign. So it will be a minus upper side and plus at downward side. Then here we have to put 2 nodes, 1 and 2. So it will be a plus, and then plus, and then plus. With a node you have to change the sign. Then in case of this system, you can see here we have to distribute how many electrons? 2 electrons from this carbon oxygen bond and 2 electrons from this carbon carbon bond. So we have to distribute equally 4 electrons, right? So 1, 2, 3 and 4. As our system is thermal system, we are going to do our reaction at 25 degrees Celsius, right? So our thermal system, so 1, 2, 3, 4, there is no excitation. Now you can see this one is the HOMO. Which one is HOMO? Psi2 is a HOMO and Psi3 star is a LUMO. Which one is? Psi3 star is a LUMO. Now this is our first system, that is our ketene molecule. Now in case of a second molecule that we are going to do cycloaddition, that is alkene, simple alkene molecule, maybe a substitute alkene molecule you can take. Now in case of a alkene molecule, if we take simple ethylene molecule, then simply 2 psi functions, psi1 and psi2, each carbon containing orbital. Here is a 0 node, sign will be same. Here we have to put 1 node, so psi1 is like this and psi2 star will be there. After a node, sign will be changed. Okay, so this is the molecular orbital diagram. Now we have to distribute how many electrons? C double bond C means 2 electrons, so 1, 2. Now which one is the HOMO? This one is the HOMO, that is highest occupied molecular orbital, and psi2 star will be a LUMO. Now there is a 2 possibilities. We can take HOMO of this system, that is HOMO of ketene plus LUMO of alkene molecule, or LUMO of ketene and HOMO of alkene molecule. Check one by one. See, firstly, if we take LUMO of this system, LUMO of this system means ketene molecules LUMO plus alkenes HOMO. What will be the condition? Firstly, make this clear that we have to make a 2 different bonds. Means we have to do suprafacial intrafacial addition. Right? Suprafacial intrafacial addition. So in case of this, we have to make this 2 different bonds, means oxygen, carbon and carbon. As 2 orthogonal p orbitals are there, one p orbital will make a 1 bond, okay, with this carbon and oxygen from this carbon, and second p orbital will make a different bond, that is second bond between this carbon and carbon. In this condition, we are going to add this ketene molecule with another alkene molecule. Now we have to do one suprafacial addition and another is intrafacial addition. Right. Now we have to see how it is formed actually. One suprafacial and one intrafacial. Suppose we have this alkene ketene molecule containing LUMO, which is the LUMO for ketene. That is our psi3 star is a LUMO. So draw that structure of LUMO. Suppose oxygen, carbon and carbon. Here is the 2 substituents, maybe chloro. Okay, now the condition is each carbon or each atom containing its orbitals. Suppose the lobes I have taken that here minus plus minus. Okay, so if I put here minus, if I rotate this, it will be a minus, plus will be at downward. This is the opposite sign, so here will be plus at upward and minus here. Just leave it as it is. There is no need to show this orbitals right now, because we have going to do just one addition. We have to take now, this one is the LUMO, right? LUMO for ketene molecule. Now we have to take HOMO of, we are doing the second reaction. Okay, LUMO of first molecule, LUMO of ketene we have already taken. Now we have to take HOMO of alkene molecule. Which one is the HOMO of alkene molecule? This Psi1 is the HOMO. Just right here, Psi1 is the HOMO. So in case of a Psi1, both orbitals having the same sign at same direction. Suppose I have to make a reaction or a bond between this negative charge, then I have to put here negative charge, negative charge. Just I am taking this orbital by reversing its side. Okay, this negative charge as upward, then positive charge will be at downward position. Now this negative charge will make easily bond with this negative charge. So this is the one type of reaction. We have make one bond. Now the second bond is formed by the second interaction. Now the second interaction is HOMO of one molecule, HOMO of ketene. Take a HOMO of ketene now. Side 2 is a HOMO of ketene. We have already done our formation of one bond. Now we have to do this formation of second bond, which is another loop. Okay. Now the second condition is HOMO of ketene molecule. HOMO of ketene molecule is side 2. That is, there is one node between this. Okay. So just I am writing here HOMO of ketene molecule. So it will be one oxygen, or there is no need to make, yes, oxygen and carbon, oxygen, carbon and carbon, same condition will be there. Here is a p orbital, here is a p orbital, and here is a p orbital. But now we have to make a bond between this ethylene molecule and this carbon, right? We have already made this bond. Now we are discussing about this bond, that will be with a different loops. Okay. Now in this case, at this carbon there is a node. Here you can see, if I am writing here plus charge, right? Here is a plus charge. We are talking about this HOMO. Here is a plus charge and here will be a minus charge. So with the node, I am writing here plus charge, minus charge. Okay. Now just the second condition, we have to take LUMO of the system. LUMO of the system is Psi2 star. Okay. So Psi2 star will be plus and minus, right? So just take plus and minus. Here is the plus, here is the minus, minus, plus. Okay. Now you can easily do the interaction between these two. See, here is a node. We don't have to write this. Here is a node. We have already put node here. Now we are talking about, yes, HOMO. So here is a node. There is no need to put any orbital here. Now we have made this second bond also. That is, one is this bond and one is this bond. So totally this interaction will give you total formation of two bonds, right? This oxygen, carbon and carbon, and we are making with alkene one bond, and this one is the second bond. Now in total this interaction, you can see this alkene you are getting 2s, and this, in case of this system, you are getting this intrafacial addition, and this is a suprafacial addition. So totally this is a 2s plus 2 intrafacial plus 2 suprafacial addition. So it is a 2s plus 2 suprafacial addition. But in this total system, this oxygen containing this orthogonal p orbital is also showing its transfer of electrons or from this side, intrafacial addition. So totally it may be a 2 intra plus 2 supra plus 2, here 2 intra plus 2 supra. So totally it may show 2 intra plus 2 supra plus 2 intrafacial addition. You can also write as per this also. Okay. In case of normal 4n electron system, it is allowed by photochemical manner by suprafacial addition, right? This is our first conclusion by our last lectures. But in case of a ketene only, there is some change, that is, whether the reaction is containing 4n electron system also, it is allowed by thermal reaction by supra intrafacial manner. Okay. Why? Because ketene containing orthogonal p orbitals, which can make a easily bond between this carbon-carbon and carbon-oxygen at a time. So it can easily overcome that barrier which is required, or that energy level which is required for the photochemical reaction by thermal way only. So this reaction of 2 plus 2 cycloaddition of ketene is possible by supra intrafacial manner in thermal condition only. Okay, to solve this example, see we have this alkene molecule and this is the system which containing a ketene, that is CH double bond C double bond O. See, C double bond C double bond O, this is a type of ketene and this one is alkene. So let's start. We have this alkene molecule and ketene molecule. This both will interact with each other. 2 plus 2 cycloaddition will be there, but just like orthogonal system, so just I am writing by perpendicular manner. So this is a ketene molecule, C double bond C double bond O, right, up to this, and it containing one carbon atom, that is this carbon atom containing one hydrogen, and remaining is ethoxide. So it is a C2H5O. This one is ethoxide. Okay, now the remaining is alkene molecule, so I am writing is as per this, CH2 and CH2, or if there is a substituent R we have taken, then you can easily write CHR. Reaction, two interactions will be there. Firstly, HOMO of alkene will interact with LUMO of ketene, and secondly, LUMO of alkene will interact with HOMO of ketene. So finally you will get, after the formation, that is a new bond formation, so you will get as per this. I am showing carbon, here is the carbon carbon bond. Now this double bond is going to change to the single bond, and this carbonyl compound, carbonyl group remains as it is. Now here we have this alkene molecule, that is CH2 and CHR. Okay, now the new bond will form between this carbon and this carbon, right, and this carbon and this carbon, and this double bond going to break at time. So as it is a concerted reaction, so you will get finally this remaining structure as it is, hydrogen and ethoxide group. Okay, there is no change. Now after this interaction, after this transition state, you will get final formation of product, that is 4-membered ring you are getting. This is a new bond and this will be a new bond that we have done. This is a CHR and hydrogen and ethoxide group C2H5O. Okay, this is a CH2. Now you can easily put it as per this 4-membered ring simply we have done. This is a double bond, then one is the R group, second one is hydrogen CHR, right, and in this carbon on this C2H5 and second will be hydrogen. So this is the final structure. We have done this 2 plus 2 cycloaddition reaction of ketene plus alkene. You are getting, so if there is a product reactant containing cis stereochemistry, then product will also having a cis stereochemistry. If it is containing trans, then product will also having a trans stereochemistry. So this maintaining of stereochemistry is done by thermally, as we are doing this reaction thermally by supra intrafacial addition in case of only this ketene molecule, because of the orthogonal p orbitals present on this ketenes. Okay, so this is an important point and mostly they have asked these questions, so just go through this. Okay, thank you.